In this video, I am going to explain you the Bernoulli's principle. But before that, I want to tell you a story of a bowl. Just imagine that there is a water flow through the pipe and in this direction. And imagine that there is a ball in the pipe with and the ball is also moving with the velocity v as exactly in the direction of the water, and the water's velocity is also v. And in this time, I am asking a question that what would be the experience of a person who is sitting in the bowl and he is also moving with the velocity v? How would he experience the nature around him? Let's pause this video and try to think about that. Okay, I am going to answer that question that he would experience as same in the case when he's in a bucket of water. Like there's two bowls, the bowl in the bucket and the bowl in this pipe should experience the same observation. Like he should see the particles around him is moving with an average velocity of 0. Bingo, that's the thing. That's I'm trying to sell you. I'm trying to tell you, not sell. If there is a particle, if you try to find, and you should excite a force into the bowl from all directions, as in the case of a bowl in the bucket. Here also there will be force. There will be force. There will be force. There will be force. And this force will depend upon how much is the pressure at that point at these regions. And this is the layer of the pipe in which each layer have different pressure. And why it's so, I already explained it in another video. If you don't see that video, then feel free to go back and check that video. In this video, I am trying to tell you the after consequence of that thing. We have a fluid particles here, a lot of fluid particles around the bowl, and you should exert a force as according to the pressure. And it is exactly like in this case. What would happen if the bowl is moved a little bit to the inside? Then the pressure at the two regions, this region and this region, is totally different. That's why the force experienced from this region and this region is also different. That's why there will be a net force to the bowl in the direction in which the net force is acting. Like if here the pressure P2 is lesser than the P1, that's why the bowl should accelerate in the direction this. Yes, this is a concept I am trying to tell you. And now we need to imagine that another thing. Now let's take a small layer of water which have a depth of dl and having an area of cross section of A. Here it is, the pressure is P2 and the pressure is here is P1. Then from the principle that we have used in the previous case, as in the case of the bowl, here the pressure is P2, so P2 into A minus P1 times A should be the net force on the small region, and the small region is the width of dl. That's why the net work done on this small region should be equal to this, and this is actually equal to P2 minus P1 times the small volume in that region. And if you imagine one more thing, that this is net work done on the small region, and what will be this work is used for? Like we know that if a region is moving from a higher concentration to the higher cross section to the lower cross section, then the velocity of the particle get increased. That's why some kinetic energy should be increased. Or if it is go to the upper layer, upper part, then its potential energy gets decreased. That's why it need to apply some work to push that water to the upper direction. Like if the pipe is in this direction, then the water in this region should go in the upper direction. That's why some work is needed. So these are the two cases. Like first is the kinetic energy, and the second one is the potential energy. These are the two areas in which this work is used for. So we can we can call it as a pressure work, like delta W. Work done, delta W will be equal to kinetic energy plus the potential energy. That's why the delta W we derive from the previous case as P2 minus P1 times the delta V, which is a volume, the small volume element, and that should be equal to half rho. This is the density of the fluid times delta V. It is a volume, and times V1 square minus V2 square plus rho delta V into H1 minus H2. These are the height difference, that's the potential energy. This is the density, and this is the volume element. This is the volume element, that is small volume element. The both sides of the equations, we can see that the delta V, so we can cancel this term. And to rewrite these equations, I can write it like this way: P1 plus rho V1 square by 2 plus rho G. Sorry, here is a G. I just forgot it about the G. There's a G is there. G H1, and that should be equal to P2 plus rho by 2 V2 square plus rho G H2. Yes, this is the thing that we are trying to derive. This is known as the Bernoulli's equation. Yeah. At this time, you may ask me one more question like, what is V1 and V2? V1 is the velocity at this position, and V2 is the velocity at these positions. And what is H1 and H2? H1 is height of this region, and height of this region. The H2 is the height of this region. Since we know that the height in these two regions are similar, so we don't need to worry about that. It is only in the case when when the pipe is in like this. The height at two different points are different. That's why we are using height in that case as well. In generally, we need to use the height to explain the Bernoulli's principle. And there is one more question you may ask me, that if we take another element, like if we take this element, we get the P1 and P2 as the pressure at the both sides, and we derive the Bernoulli's equation. What would happen if we take another element like this one? Here it is P3 and it is P2. Then what should be the things? And the velocity is V2 and the velocity is V3 and the height is H3 and the height is H2. If we try to derive the Bernoulli's equation by using the same principle, like here is a force in this direction, here is a force in this direction, this force is greater than this force, that's why the particle, this small dl element will move in this direction, we would end up with the Bernoulli's equation like this. And the P2 and P3, like in the previous case P1 and P2, and we know that this element and this element are same. So what it actually means? It meaning that if we take any another element here, we can take another element here, all are connected. That's why we can derive a lot of equations like this, like each one is connected. So basically, this thing, it is a constant. We no need to worry about anything else. This is actually the Bernoulli's theorem. The Bernoulli's theorem is actually saying about this thing, that is the energy is a constant. The total energy is a constant. That is height energy and the velocity kinetic energy and the pressure energy, both are same. By using these equations, we can solve a lot of problems. This is actually the Bernoulli principle. Bernoulli's. In this video, I am trying to tell you an very imaginary way of Bernoulli, imaginary way in which you can imagine the things, what should happen inside the fluid flow. If you try to imagine like this, you may get a good presentation, you may get a good quality of acceptance of the concept of the Bernoulli's principle.